Okay. Good afternoon, everyone. We shall get started. Yeah, thank you. So first of all, a reminder, our homework one will be due on this Friday midnight. Just make sure you submit on time so that you won't get any late penalty, those kind of stuff. Right? Question? Oh, Tuesday. Okay, okay. Yeah, right. Thank you. Oh, should be tonight. Okay. Yeah. Okay, sorry. Yeah, I kind of like messed up with my another class schedule, right? But anyway, just a reminder, this homework is really simple. If you really spend some time, like it won't take you more than half an hour and 2 minutes to take a picture and upload. Just don't forget to upload it. I mean, that will cause some kind of like late penalty and so on. And also, question? It's due, I believe due should be 11:59 p.m. tonight. Yeah. Oh, 28. Okay. Yeah, anyway, yeah. Yeah, it's either, okay. So we got 2 weeks. Okay. Sorry, I can't memorize exact date, but just let you know, it's just about 2 weeks. If it's not, oh yeah, should be, yeah, then that should be the next week, right? So just reminder, don't forget. Right. Okay, sorry. Oh, another thing is that this week's quiz will be available after today's class. Again, you don't need to take it right away. We kind of like trying to release the quiz earlier to give you sufficient flexibility for the choices, but just don't forget to take it. And you will see that there is only one problem in this quiz. Ask you to calculate some probability. But if you're worried that, okay, your number or your fraction is not correct, trying to write some explanation in the question 2, which is just the text box, right? And after that, we'll check. Like if you got a full grade, we won't look at your your textbook. If you don't have a full grade, then we'll take a look later and see if we can give you some partial points on that. Okay. Okay, so let us continue with the. That's a little bit. Let us continue with the independence, right? So we talked about in the last lecture the definition of independence, right? So it has a very natural or very intuitive explanation. Like we say, even A is independent of even B if the conditional probability of A given B is the same as the marginal probability of A. So what does it mean? Like what does English mean, right? In English, it means that, okay, the occurrence of the even B have nothing to do with the chance that even A happens. So that's why we write it in this we write it in this way, right? So and then it comes to our mind, right? What's the definition of conditional probability? Right? This is something we must be very, very familiar in our mind, right? So what's the definition of P, A, condition on B? Anyone recite the formula? Yeah, what's the definition of P, A, condition on B? Yeah, definition, right? But mathematically, how we're gonna, calculate that? Yes, exactly, right? That's the definition, right? You don't need to ask why, but this is the definition, right? So when we calculate this conditional probability, we're just calculating the ratio, right? The ratio between the probability of the intersection between A and B and the marginal probability of B, right? We also have given some kind of visualization for this, right? So if you look at this, right? So if this is your A, if this is your B, so the conditional probability of A, conditional B, means that, okay, I'm gonna calculate the area, which is the probability, right? Over the overlapping part, A intersection with B, and then divided by the whole area of B, right? That is called conditional probability, right? Okay, so if this conditional probability happens to be the marginal probability of A, that means this ratio is equal to the area covered by A, right? That means A and B are independent, right? Okay. And we show some like kind of interesting, starting from this original definition, right? We show some like interesting equivalent results, right? And for example, if we write down the definition of P of A conditional B, which is, as we just recall, right? So it's a P A intersection with B over P of B equals to P of A, right? So if you multiply P of B on both sides, we obtain another results, which are totally equivalent, right? That means like the probability of A intersection with B is equal to the product of the marginal probability of A and the marginal probability of B. So this derives another definition of the independence. We say A and B are independent to each other if their joint probability, this guy, is the same as the product of their respective marginal probabilities. So this is another commonly used way to define the condition, the independence, right? In fact, I mean, through my study, this is always in my mind. Okay. And on the other way around, right? If you continue to do some kind of derivation, right? So starting from the equivalent definition we just had, right? So intersection, the probability over the intersection between A and B equals to P of A times P of B. Now you divide both sides by P of A, right? You divide by both sides by P of A. So you see the left-hand side becomes the ratio of P A intersection with B and P of A, right? And the right-hand side is P of B, right? And then using our definition of conditional probability again, the left-hand side actually is another conditional probability, right? Remember, the conditional probability is just a fraction, right? The guy who is on the denominator will be the conditional part, right? So now P of A is in the denominator. That means, okay, it is representing the conditional probability of B conditional on A, right? So now we can see it gives us a third definition, which is the conditional probability of B conditional A is the same as the marginal probability of B. This is the third equivalent definition of the independence, right? So you see that, right? So this one is original one, right? And through our kind of like a simple arrangement, right? Rearrangement, we get a symmetric definition. Then we observe that the independence, the definition of independence is a symmetric definition, right? So the conditional probability of one event A condition on the other event B is the probability of A itself, is equivalent to say the conditional probability of B conditional A is the same as the probability of B. So in other words, if you say the happening of A has nothing to do with B, it is equivalent to say the happening of B has nothing to do with A. This is an interesting point, right? Right. But some students asked me like last week after class, it's very interesting. Like saying, okay, if there's some kind of causality relationship between B, for example, A is a causal effect of B, will this symmetric property still hold? Well, actually, that leads to a deeper question, right? So right now we're talking about probability and statistics. All those dependency or independencies are bidirectional, meaning that we say A is independent of B, that means B must be independent of A, right? A depends on B, that means B also depends on A, right? That is from the statistical discipline, or this particular mathematical framework will define dependency in this way. But in the future, say if you want to go to grad school or doing some like PhD program, if you want to, there's a new branch of statistics. It's called causal inference or causal learning. They're gonna give you a different definition of dependency. Okay, but just like you, it's out of our class scope. Okay, so and then we in the last lecture we went through two problems to show how do we calculate the conditional probability, right? So actually we have three problems. We only got time to finish two, right? So let us finish the third problem to refresh our mind, right? To familiarize ourselves in computing conditional probability. Okay, let us look at the problem, right? So assuming we got a power system, it has two parts. One is main power supply. The other is an auxiliary power supply. We can view like this auxiliary is kind of like a additional part, right, to the main power. So we have the probability that the main supply fails is 10%. And the auxiliary supply also has a chance to fail. But right now the information is here, right? If main supply is working, then the auxiliary supply fails with 10% chance. If main supply fails, then the auxiliary supply will have a larger chance to fail, which is 15%. Is it clear, everyone? Okay. So now we want to consider two events. One event is called auxiliary supply fails, like we denote as A. The other event is called main supply fails, is denoted as event B. We want to check whether A and B are independent to each other, right? How do we verify this? How do we verify this? Whether A and B are independent to each other or not? Yes. What we need to verify, right? We need to calculate, right? Yeah. But yeah, but the idea is just like what he said, right? So we use definition, right? If we say A and B are independent, then we must have P of A equals to P of A given B, right? So then the remaining is just a calculation, right? Following the definition of the conditional probability and marginal probability, we'll just look at whether the two quantities are identical, right? So, okay. So first, what is P of A given B? What? 15%, right? So it actually has already been given the problem, right? So we know that when main supply fails, auxiliary supply fails with 15% chance. That just tells us that the probability of A given B is just 15%, which is 0.15, right? So the remaining is how to compute the marginal probability of A, right? So we have a little bit like a sophisticated way to, algebraically to calculate that, right? We're not gonna do that again. We're gonna use a more intuitive diagram to show this, right? Remember, we talk about how to use tree diagram to expand all passes through the result, right? And we just add the probability for every pass to get marginal probability, right? We're gonna just leverage this again, right? So we need to consider first the event, whether the main supply fails or work, right? So we got two chances, right? Main supply. So we know the main supply will got 10% chance to fail. So it means that it has a 0.1 probability to fail, right? And also it has another branch, which means that it is working, right? So what's that probability? 0.9, right? Yeah. Now we consider, given different situations, what's the chance that the auxiliary supply fails or work, right? So first, given that main supply fails, right? Sorry, this is about auxiliary, right? So given the main supply fails, right? What's the chance that the auxiliary fails? %15%, right? Yeah, that's just given by the problem. Right? When main supply fails, the auxiliary got 15% chance to fail. So we got here 0.15. Then when main supply fails, what's the chance the auxiliary is still working? What's that chance? 0.85, right? It's just 1 minus 0.15, which is 0.85. Similarly, consider another case where the main supply is working, right? And then we look at the status of auxiliary system. It still has two possible status, fail or failing or working, right? So given the main supply works, right? What's the chance that the auxiliary still fails? I heard that. 10% chance, right? It's here. It's 10% chance. So this is a 0.1, right? Then what's the chance that the auxiliary is still working? 0.9, right? Okay, so our event A is talking about, okay, overall, in whichever situations the auxiliary supply fails, right? So that means we just look at along all the paths, the auxiliary system fails, right? We got two paths, right? One is here, one is here. So that means the probability of A equals to the summation of the probability for two paths, right? So the first path will be 0.1 times 0.15. The second path is 0.9 times 0.1, right? And then we just need to do a little bit calculation, right? So this guy is, the first term is 0.015. The second term is 0.09. So the final result is 0.105. Am I correct? Right. Okay, so now we got our marginal probability of A, which is 0.105, right? And our conditional probability, which we know here. Oops, I don't know why it's become so small. Let me rewrite it. The conditional probability now is 0.15. What conclusion can we make? Are they the same? No, they're not the same, right? They're quite different. Then that means the conditional probability is not equal to the marginal probability. So A and B are not independent of each other, right? In other words, A and B are independent, are independent, right? Any questions so far? I mean, this is just through the calculation, right? But when we write down this analysis, when we draw this diagram, you see intuitively A and B should be dependent on each other, right? Because you see the probability of A actually contains the cases that your main supply fails and your main supply works, right? And this calculation is kind of relying on whether your main supply is failing or not, right? So intuitively, it should have some kind of dependencies, right? But it's not always like this. It also has something to do with all those conditional probabilities. But in this case, they're not the same, right? So if you could remember, if you connect to the example we mentioned, we walked through in the last lecture, when you change the conditional probability to a way such that this path, the choice of the path actually has nothing to do with your final probability, then A and B will become independent to each other, right? So if this example sounds like blurred or you can't remember the details, that's fine, right? You can going back and review this example to see like how when you change the number of the conditional probabilities along each path will eventually make the two events from being dependent to be independent to each other. Okay. Any questions so far? Yes, yes. That's why I mentioned this picking ball problems in our last lecture. Remember, we also draw this fancy tree diagram to show how we compute the probability of A and the probability of B. Of course, A and B represents different events. right? And at the beginning, definitely, P of A is not equal to P of A conditional B. They are not independent, right? But then when we change the setting for the earn2, right? Remember, previously the earn2 was set to have two black balls and two white balls, right? And they're different, right? And A and B are not independent. However, when we set earn2 to have like 8 black balls, right, and 6 white balls, we'll calculate using exactly the same procedure. You find that P of A will be equal to P of A given B. So A and B turns out to be independent, right? That's why, like, if you look at the tree diagram, it's very similar to the one we just drew here, right? The only reason that changes because you make this conditional probability along those paths different, right? And by setting those numbers, you kind of like are not able to differentiate which paths give you the final results, fail or red ball, whatever. That's why I'm requesting you guys, like, after the class and look back at our previous examples and to see how those settings, right, the calculation procedure won't change, affect your conclusion. Any other question? Okay. Very good. So the next thing we would like to discuss is that let us think about like intuition about independence, right? We say A and B are independent. Literally, it means like, okay, B happens, the chance of A happens has nothing to do with A just happens, no matter whether B happens or not, right? In other words, the chance of A happens will have nothing to do with whether B happens or B not happens. And B happens represent even B. The B does not happen is represented by the complement of B, right? Right? So remember, that's our definition, right? So B represent some kind of event happens, right? And the complement of B, BC, represents that event doesn't happen, right? Then we say A and B are independent. Intuitively, it should be like, okay, the chance of A happens has nothing to do with B happens or B not happens, right? In other words, according to the definition, A and B complement should be independent to each other as well, right? That's our intuition, right? It's like, okay, tomorrow I get up late, right? I get up late, or no, tomorrow I get up early or I get up late has nothing to do with tomorrow there will be a weather, right? There will be a storm, right? And not that my getting up late has nothing to do with the storm happens. It should also has nothing to do with storm doesn't happen, right? That's the intuition. Then the next thing for us is to check whether this is correct, right? And mathematically, we should arrive at this conclusion. Otherwise, it's weird, right? It doesn't reflect our natural sense about the world. Okay, then let us do some kind of like mathematical justification. So we're starting from this definition of the independence, right? The joint probability of A and B equals to the product of the marginal probability of A and the marginal probability of B, right? Remember, we have several equivalent definition of the independence, right? This is just one of it. I just pick up pick it up, right? Okay, let's see what can we do out of this definition. So first, from the intersection of two events, right, we can apply the definition of the intersection. The intersection of A and B can be written as the set difference. It can be written as A subtracted by the complement of B. Right? This is some rule we have previously introduced. Right? If you don't recall it, that's totally fine. We can just look at previous slides. You will find it. Right? But here we to strengthen to make our feel comfortable, I will just draw a figure to show why this is correct. So consider this is your sample space, right? So this is your A. And this is your B, right? And this guy is the intersection between A and B, right? And now let us look at this guy, right? So we claim that the intersection between A and B is equal to A, the set difference between A and B complement, right? So what's the set difference of B? You just look at all the other area excluding B, right? So it will be those guys, right? Right? All the other space in omega excluding B, right? Now, if we look at A minus BC, what does it mean? What's the definition of set difference? Yeah, exactly, right? That's the set difference definition, right? Set difference means that I'm gonna excluding the common parts between two sets, right? So here the two sets, one is A, the other is a complement of B, which is those radiation part, right? So if we exclude the common parts in A, you will see it also arrives at the overlapping part, right? That's why it is equal to A intersection with B, right? That's a simple way to show this rule, right? So that means we can rewrite this as the probability of A minus B complement equals to P of A times P of B when A and B are independent to each other. Right? So next, let's see what we can get, right? So if we further look at the left-hand side, right, I'm gonna use red ink, right? Left-hand side, we can apply the difference rule, right? This is called probability difference rule, right? So the probability of A subtracted by B complement is equal to the difference of probability A and A intersection with B complement. Okay. Again, this rule has been introduced before. And if you feel uncomfortable, that's totally fine. You can just assume this is correct, right? This is just some mathematical fact. Of course, we can go back to look at why this is correct, right? So through the Venn diagram here, right? So as we mentioned, the probability of A minus B complement is actually the area of this overlapping part, right? This is actually the probability of A intersection with B, right? This is what we just discussed, right? And then this area is equal to the whole area of A, right? The whole area of A, which is P of A. Then subtracted by the area of A, the area over A intersection with B complement, which is this part, right? Right? If you do the intersection between A and the B complement, those radiation, light blue radiation part, right? The intersection will be this part, right? And that means like you just subtract the whole area of A by this blue part, right? With blue lines covering, it will be the area of this red overlapping part, right? That's how we arrive at this, right? This is a good way to understand how these probability rules are arrived, right, are derived. Any questions so far? Okay. So let us continue, right? So now we have, if A and B are independent to each other, we claim that P of A is subtracted by P of A intersection with B complement equals to the product of P of A and P of B, right? Now we just need to do a little bit an actual manipulation over P of B. Remember, P of B equals to 1 minus the probability of B complement, right? This is another probability rule we introduced before, which is called complement rule. It's also fairly straightforward to understand if we just draw a Venn diagram, right? So this is B, right? Suppose this is B. And the probability of B, you can visualize as the area inside B, right? Of course, it is 1 minus the area of B complement, right? And 1 is, of course, is the probability over the entire sample space, right? Which is always 1, this is by definition, right? Does it make sense? I mean, if you feel you still feel like uncomfortable, a little bit confusing, doesn't matter, because you can replicate this derivation by looking into those rules we placed in a few slides, in previous lectures. You just contrast that, apply that. That's it. Here, just to give you a sense, right? Okay. So now, applying the complement rule, we represent P of B as 1 minus P of B complement, right? And of course, we can rewrite this product as P of A subtracted P of A times P of B complement, right? This is just a distributive law, right? In the multiplication, right? So now we see that there's a common factors on both sides. You can cancel it out. Then you just multiply both sides by -1. We end up with the result here. The underlying result tells us that the joint probability of A intersection, the joint probability of A and B complement is the same as the product between P of A and P of B complement. What does it mean? It means, according to the definition, A and B complement are independent to each other. Right? That's our definition, right? The independent definition is that if the two events are independent to each other, then their joint probability, meaning the probability of their intersection, is the same as the product of their respective marginal probabilities. And here we can see that the probability of A intersection with B complement is the same as the probability of A, marginal probability of A, right? Marginal probability of BC, B complement. That means A and BC, B complement, are independent. Any question? Okay. This gives the definition that A and BC are independent, right? So now we can give a more comprehensive definition of independence, right? We claim that, or we define that, events A and events B are independent if any of the following four conditions are whole. First, that's our very original definition, right? The conditional probability of A, conditional B, is the marginal probability of A. Or symmetrically, the conditional probability of B, conditional A, is the marginal probability of B, right? So they're actually symmetric to each other, right? The happening of B has nothing to do with happening of A. And vice versa, right? The happening of B has nothing to do with happening of A. The third one is the probability, the joint probability of A and B is the product of their respective marginal probabilities. These three we have derived from the beginning, right? And then later, you can replace B by B complement and throw them into all these three. Oops. They are representing the same thing. They're still defining the independence between A and B. Does it make sense? Any questions so far? Okay, hope everyone has a thorough understanding about definition of independence and also all those relationships. Right? They are all equivalent to each other. Right? Okay, so let's just take a rest for 5 minutes and let us continue. Mm-hmm.
We have to consider like the omega, like the whole sample space. Can I just write?
Yeah, you don't need to draw this wind up. You can just use set
Something like this.
Yeah, something like this or B complement or something like that. Yeah, I mean all kinds of set operations.
Yeah.
You feel free to construct that even.
But I don't need like omega in the
I think so. You don't need omega. It should be like complement, intersection, union.
Yeah.
Or set difference should be sufficient.
Okay. Yeah. Thank you.
Yeah.
Three balls.
Yeah.
Here it says what is A complement and B complement. I just don't know where we got those from.
This is problem 3 or problem
think it's problem three.
Problem three?
Yeah. It says C.
Oh. Okay, okay. Yeah, in this case, we need to specify what is the sample space. Like remember, we take two balls, right?
Yeah.
And one by one without replacement,
Yeah.
right? You need to list all possible outcomes, right? That
Okay.
should be like pairs of ball indexes, right?
Yeah.
Like 1, 2, 1, 3, 2, 1, 2, 3, and so on, right? And you have like set representation for A, right? And A complement that you're gonna exclude them from the whole sample space.
Okay, so A would be the whole sample space.
The A is not necessary to be the whole sample space, but if you want to compute A complement, you need the whole sample space.
Okay.
You need to first write down what is the whole sample space.
Okay.
Yeah.
Thank you.
Okay. So everyone, let us continue. Okay. So next, we're going to talk about another concept. It's called total probability. Right? So later we will see total probability actually gives an exact justification about the tree diagram we used before. Right? Okay, so what is total probability? So it actually considered how we're gonna involve a set of other events to calculate the marginal probability of one event. Like say, if I want to calculate the marginal probability for some event A, right? Then perhaps it's hard to directly calculate that. Then I'm gonna involve a set of other events like B1, B2, B3 until Bn, and use them to help calculate P of A. So it's actually a very, very commonly used mathematical method for the probability calculation. Right? So let's see the formal definition first. Right? So first, suppose we have a sample space omega, which represents all possible events, right? All possible outcomes of your random experiment. Right? Then we consider a set of events B1, B2 to Bn, which kind of like partition omega. By partition, it means that all those events B1 through Bn are pairwise disjoint, meaning B1 won't overlap with B2, B3, B4 until Bn. B2 won't overlap with B1, B3, B4 on the other, right? No event will overlap with any other event. This is called pairwise disjoint. And second, if we do a union of those events together, they form the whole sample space. That is called partition, right? It's like you got a pizza, right? And then you just partition them into several pieces, right? And you distribute those pieces to your friends, onto everyone in the party, right? You don't expect that two pieces will overlap, right? And if you have this set of events in your hand, like B1 through Bn, then we can calculate the marginal probability of A. Remember, A has nothing to do, not has nothing to do, but the A is not among B1 to Bn. A is like another event. The marginal probability of A can be decomposed in the following. We can first compute P of B1, then times P of A conditional B1. Then plus P of B2 times the conditional probability of A conditional B2. You just add all those products together until Bn. You get your marginal probability. This is called total probability. Any question regarding the definition? Okay, so let's see some like a concrete example. Question. Intersection with what? A intersection with the sample space. The right hand side. Yeah, so A intersection with sample space is A, right? Because A is just a subset of the whole sample space. Yeah, I guess you want to show this, right? You want to prove this. Yeah, we're not gonna go through a proof, but yeah. The idea is showing if you want to prove that, that is the way you prove that, right? But let us first make sure we are clear about the result, right? Okay, so here's a concrete example to show how this total probability expresses, right? So suppose this big circle is our sample space omega, right? Like a big pizza, right? Now we got 4 events, B1, B2, B3, B4. You kind of partition this pizza into 4 pieces, and we name it counterclockwise, right? B1, B2, B3, B4. They are non-overlapping, and their union is the whole sample space, right? And then if we want to compute the probability of another event A, which is represented as a blue circle here, right? So that means you want to compute the area of this. Maybe I should use blue line. We want to compute this area of this smaller circle A, right? And the total probability tells us we can calculate P of A in this way. We can first calculate the marginal probability of the first piece, P of B1, times the conditional probability of A given B1. Then add the marginal probability of B2 times conditional probability of A condition on B2 plus the marginal probability B3 times conditional probability of A condition on B3 and plus, sorry, it's a little bit tedious, but the marginal probability of B4 times the conditional probability of A condition on B4. That's what the total probability tells us. Right? So someone asked why, right? It's actually very intuitive if we look at through this Venn diagram, right? So first, if you look at this guy, according to the definition, this is what? P of B1 times P of A condition on B1. What's that? Yes, exactly, right? Remember, it's just the reverse. If you just look at the conditional probability definition, right? It's just the reverse, another description, right? It's just B1, sorry, intersection with A, right? So from the figure, it is just the area of the overlapping part between B1 and A, right? Does it make sense, right? B1 intersection with A, the probability. It's just the overlapping area between A and B1, right? And similarly, the second term is just calculating the overlapping area between A and B2, which is this part. Does it make sense? And third one, again, third one is essentially the probability of A intersection with B3, right? It's just the area of the overlap between A and B3, right? This guy. And the last term is the area of the overlapping region between A and B4. Right? Now we see the whole area of A is just the summation of the areas over these 4 subregions, right? That is the straightforward explanation of this total probability rule. Any question? Okay. So there is one special case. If we just consider 2 events, right? If we just come up one event B, right? And then we know B and B complement also form a partition of the whole sample space, right? B and B complement will be all the other region that excluding B, right? So then if we apply this law of total probability, we get this. Right? P of A equals to the marginal probability of B times the conditional probability of A given B plus the marginal probability of B complement times the conditional probability of A conditioned on B complement. Right, that's just the straightforward application of the total law of total probability we just mentioned. Right? Okay, so now let us try to use this definition to calculate something, right? As an example. So actually, it comes to our previous problem, right? Now with total probability, you see everything makes sense and also connects to our tree type diagram way of calculation, right? So to Ernst scenario, N1 has 4 black balls and 3 white balls. N2 has 2 black balls, 2 white balls. And the random experiment is done in this way. You're gonna first randomly pick up an urn, meaning that you got half chance to select urn 1, you got another half chance to select urn 2, right? And then from the urn you selected, you randomly pick a ball. So now we want to look at what is the probability the ball is white, right? So we can define this event as A, right? A is you pick up a white ball. Is everyone clear about this? Yeah, we're all familiar with this, right? Okay, so to calculate P of A, right? Let us define an event. The event B is defined as you pick urn 1. Then what is B complement? What does B complement represents? Yes, exactly right. So B complement means you pick urn 2, right? So now let us try to leverage this total probability, right? So just copy this formula, right? We know P of A equals to P of B times P of A conditioned on B plus another case, B complement, right? Which is P of B complement times the conditional probability of A given B complement, right? And then let's see, what is the probability of P of B? One half, right? That's our problem, right? You random pick up and earn, right? So it's one half. And what is the conditional probability of A condition on B? 3 or 7, right? Because that is conditional on you pick up earn 1. You got 4 black balls, 3 white balls. So your chance of picking up white ball from earn 1 will be 3/7, right? Let's see. Let's try to fill numbers for the remaining terms, right? So what is the chance of P? What is probability BC? One half, right? Random pickup. And then what is the condition probability of A condition on BC? One half, right? That means the condition on you select earn 2. What's the chance you pick up white ball, which is, well, let me be more naive, is 2 or 4, right? Which is one half, right? So now let us just calculate the number, right? It just adds them together is 3 or 14 plus, well, 1 over 4, right? So you see this way you calculate P of A is pretty straightforward, right? So this actually corresponds to our tree type diagram, right? It's like, okay, I'm gonna look at first which earn I'm picking, right? I got one chance to pick up earn 1, and then I got 3/7 chance to pick up a white ball, right? Of course, given earn 1 is picked, I also have a 4/7 to pick up a black ball, right? And then there's another case like you got another chance, like half to pick up earn 2. And given earn 2, you got 2/4 to pick up white ball. You got another 2/4 to pick black ball, right? That's pretty much how we draw this tree diagram, right? And if you want to look at the marginal probability of picking a white ball, you just look at all the paths that give you the white ball, right? And add them together. So you see, this is exactly reflected in our calculation of the total probability. Right? So in other words, like total probability essentially can be visualized through this tree diagram. Any questions so far? Okay. Yeah, let's try another problem, which we have seen, right? Let us try to use total probability to calculate this, right? Again, we want to look at this power system. We got the main power. We got auxiliary power supply, right? The main power supply fails with probability 10%, and auxiliary power fails under the probability under different situations are as follows, right? When the main power is running, it has 10% chance to fail. When the main power fails, it has 15% chance to fail, which is lighter, which is heavier because it's overload, right? Then we want to compute what is the probability the auxiliary power will fail, right? Let us define this as A. Then we can define another event B as main power running. Right? Oh, sorry, main power failed. Okay. So we have a B complement. What does B complement means? Not fail means that it's running, right? It's working, right? So it's just the main power running. Again, calculation, we can apply the total probability, which is P of B times of P of A condition on B plus P of B complement times P of A condition on B complement, right? Then the remaining things for us is just to fill out number, right? So what's the chance that, what is P of B? What is P of B? %, right? It's here. 10%. And then what is P of A given B? Or condition on B? .15, right? It's here. When main power fails, it has 15% chance to fail, right? So it's 0.15. So this one is, what is P of B complement? 0.9, right? So here tells us that main power supply fails with probably 10% chance, then with 90% chance of it is working well, right? So it's 0.9. And with the conditional probability of A given B complement? 0.1 is here, right? So we just add them together, which is 0.015 plus 0.09, which is 0.105, right? You see it's the same as we calculate a moment ago, right? Here, it's the same. But this time we just use total probability. At that time, we just draw this tree diagram, right? They're essentially the same. Okay, so let's stop here today, right? And see you on Thursday.